In this lecture on chapter 17, we're going to talk about how chemicals react. Now, as an example, we've seen in previous lectures how if you have oxygen and hydrogen, it's possible to mix them together so that you form water, H2O. How does that happen? What do we know about the rules that define what kinds of reactions can occur? That's what this chapter is going to be all about. Now, it turns out that we can actually set up equations, a specific kind of an equation called a chemical equation that shows you how different chemicals can react and combine with one another. And we're also going to talk about how we can count the numbers of atoms involved in reactions. Now, the numbers of atoms involved in a typical chemical reaction are so big, you couldn't possibly point at them and count 1, 2, 3, 4, 5. And so the way we actually count how many atoms or molecules are involved in some kind of reaction is we use the mass of the material made up by those atoms and molecules. And so we're going to see how we can actually count atoms by measuring their mass, atoms and molecules by measuring their mass. And that's really what this video is going to be about. In the next video, we're going to look at how different reaction rates occur with different kinds of chemical reactions. We'll talk about how catalysts can be used to speed up chemical reactions. We'll talk about how that relates to the energy involved in a chemical reaction. And finally, we're going to talk about something called entropy, which is a pretty interesting thing, and we'll get to that in the next lecture. But in this lecture, we're going to mainly focus on these first two, on how chemical equations work and what they tell you, and how we can count the number of atoms involved in a chemical reaction by measuring the masses. Okay, here we have a basic chemical reaction, and it's the simple one that I mentioned previously. I've got two molecules of molecular hydrogen. That's two hydrogen atoms bonded together. We've seen that hydrogen forms H2. And we've got one molecule of molecular oxygen. That's two oxygen atoms bonded together into a molecule. And when you add these together, this two molecules of molecular hydrogen plus one molecule of molecular oxygen, it yields two water molecules, two molecules of H2O. Now, the things that you start with are called the reactants. So in this particular reaction, the reactants, the things that are reacting together, would be the hydrogen and the oxygen. And then they have their interaction, they combine, they rearrange, and you end up with what are called the products. In this case, the products would be the H2O, the water. And of course, we want to recall, during a chemical reaction, one or more new compounds are formed as a result of the rearrangement of atoms. So that's what's going on here. I've got these two hydrogen molecules and this oxygen molecule. They interact with one another, they react, and then you end up with the atoms rearranged. So these hydrogen atoms are broken apart, the molecules are broken apart into their individual atoms. These atoms of the oxygen molecule are broken apart, and then those atoms recombine into something new. So I start with hydrogen and oxygen, I end up with water. Now, in each of these, you'll see a little G following them. That's just to let you know that the hydrogen is actually gas. Under normal conditions, you're going to end up having hydrogen gas, oxygen gas combining. It is possible to have, for example, two solids combine, or a solid combining with a liquid, or something like that. And so you might, instead of a G for gas, you might see a little S for solid. And so anyway, if you see the things in parentheses, that's telling you what state of matter that you're talking about. And in your assigned reading, they go through a lot of options what could be there besides G, not just solid, liquid, and gas. But in any case, look to your textbook for that. Now, the one thing that's truly fundamental about chemical reactions is that the mass of all the things you have involved in those chemical reactions must be conserved. This is called the law of mass conservation. And what it tells us is that no atoms are gained or lost during any reaction. In other words, the number of atoms you have when you start is the same as the number of atoms that you have when you end up. So in that previous reaction, we had 2H2 plus 1O2 yields 2H2O. Now, how many atoms do we have before the reaction? So everything to the left of the arrow is before the reaction. So the arrow, which we say is the yield symbol, that is indicating that the reaction is taking place. Everything to the left is what you have before the reaction, and everything to the right of the arrow is what you have after the reaction. So how many hydrogen atoms do I have before the reaction? I've got 2 sets of H2, so there's 2 hydrogen atoms here. I've got 2 sets, so that gives me 4 hydrogen atoms before, and then I have 2 oxygen atoms after, because I've got 1 oxygen molecule that has 2 atoms in it. So before, I've got 4 hydrogens that I'm starting with, and I've got 2 oxygens that I'm starting with. Now what do I have over here? I've got 2 water molecules, each with 2 hydrogens and 1 oxygen. So the 2 doubles everything, so that leaves me with 4 hydrogens and 2 oxygens. So what I have here is 4 hydrogens after the reaction, 4 hydrogens before the reaction. I've got 2 oxygens before, 2 oxygens after. And so the mass of hydrogen is the same, the mass of oxygen is the same before and after the reaction. So we can sum this up and say the number of times atoms appear before the arrow must be equal to the number of times they appear after the arrow. So let's look at another example. So here we have this configuration of 2 different molecules, each with 3 atoms in it, and they interact, and you end up with 3 molecules, each with 2 atoms in it. And the question says, in total, how many atoms are represented in the following schematic for chemical reaction? Well, obviously the answer is 6, C. We can see that because each one of these little dots is representing an atom bound into these different molecular configurations, and in each case I've got 6. And I know if there's 6 atoms before the reaction, there must be 6 atoms after the reaction. So I don't have to count up twice. I can just count on one side or the other and figure out how many atoms I have. And remember, the things that are existing before the reaction, these are called the reactants, the things that are reacting. And the things you end up after the reaction, the things that are produced, are called the products. So we have the reactants, we have the products. Okay, here's another example. Is this reaction balanced? Yes or no? Well, let's figure it out. So each of these different blobs represents an atom, and each color represents a different species of atom. So maybe the pink ones are hydrogen, and maybe the yellow one is oxygen, maybe the blue one is carbon. It doesn't matter what they are, but each different color represents a different kind or a different species of atom. So is a reaction balanced? You'll know that it's balanced if you have the same number of each kind of atom before as you have after. So let's count up the pinks. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pinks. That's on the left side. How many do we have on the right side? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 pinks on the left, 14 pinks on the right. That is balanced. What about the yellow? I've got 1, 2 on the left. I've got 1, 2 on the right. That's balanced too. What about the red? 1, 2. Over here, I've got 1, 2. That's balanced. And finally, the blue. I've got 2 of the blue on the left, 2 of the blue on the right. So my answer is that yes, this is a balanced equation. You have just as many atoms of each kind on the left as you have on the right. Okay, continuing with this, the next question is how many quote-unquote diatomic molecules are represented? Remember, a diatomic molecule is one that contains two atoms. And so I see here there are two diatomic molecules on the left, and there's only one diatomic molecule on the right. Now, what does it mean that there's a difference? Well, what it means is that one of these guys, maybe this one here, it actually broke apart in the chemical reaction, and these two atoms got rearranged and moved over to some of the other molecules on this side. But this guy right here, he didn't react. So he just kind of hung out during the reaction, and he didn't get broken apart. He didn't do anything. He just kind of was hanging out there. So the next question we have here, another example, is the following chemical equation balanced? I've got one molecule of CH4, that's actually methane, combined with two molecules of molecular oxygen, that's two oxygen atoms bonded together, so I've got two of those, and they have a reaction, they combine together and rearrange, and then after that happens, I end up with two molecules of water plus one molecule of carbon dioxide, CO2. And the question is the following chemical equation balanced? What does that mean that it's balanced? It means that it's a possible reaction, right? If the atoms were not balanced, in other words, if I had more hydrogen over here than I started with, that would mean that I had created hydrogen out of nothing. I just magically made hydrogen appear. And that's not allowed. So, in a chemical reaction, the mass is going to be conserved, and so you can't have any more or any less than you started with. So, I've got one CH4 plus two O2. Does that balance with two waters and one carbon dioxide? The answer is yes, because the same atoms appear before the equation and after. And when I say the same atoms, I mean the same number of each kind of atom appears before and after. Let's go through that and show that that's true. So, on the left-hand side, we're going to look at all the atoms we have and count them up. We have one carbon, four hydrogen, and four oxygen. There's two for each molecule. There's two molecules. 2 times 2 makes 4. So again, we've got one carbon, four hydrogen, and four oxygen. And of course, that is on the left side of the equation. Now, on the right side of the equation, I've got one carbon, I've got two oxygen over here, I've got two hydrogen and an oxygen there, but I've doubled that, so that gives me 4 hydrogen and 2 oxygen. So I've got 4 hydrogen altogether, I've got one carbon altogether, and then I've got 2 oxygen here and 2 oxygen there. That makes 4 oxygen altogether. So I end up with the same number of each kind on the right side as well. I've got one carbon, that's that guy. I've got 4 hydrogen, which is 2H2. And then for the oxygen, I've got the 2 oxygen from there and the 2 oxygen from there. That makes 4 oxygen total. And I can see that the numbers are the same on each side of the equation. So the equation is indeed balanced. Now the next thing we want to talk about is how we can mathematically express these chemical equations. And what we want to do is talk about how you can count the number of atoms and molecules there are in a reaction in the real world. Because if I just grab, certain chemicals and mix them together, there are huge numbers of atoms and molecules. You could never put them under a microscope and count them all out individually. But what we do is we use mass. And in your textbook, there's a great analogy to help you understand this idea. And what they say is if I've got a box, for example, that has ping pong balls in it, and it's just filled with ping pong balls, and I've got another box that's filled with golf balls, if I take a single golf ball and I get its mass, and I take a single ping pong ball and I get its mass, what I find is that the golf balls have 20 times the mass as the ping pong balls, or 20 times as massive. And so, if I've got two boxes, each 1 kilogram, or the contents are each 1 kilogram, and one of them is ping pong balls, and the other is golf balls, and if I have the same amount, what I know is to make up a kilogram of golf balls and to make up a kilogram of ping pong balls, I actually need 20 times as many ping pong balls as I have golf balls. And so that's a way of counting what we call relative numbers. And so I know I've got 20 times as many ping pong balls as I do golf balls in that kilogram. By the same token, if I want to have an equal number of golf balls and ping pong balls, I could, for example, have 1/20th of a kilogram of golf balls, 1/20th of a kilogram, and then if I had 1 kilogram of ping pong balls, so this would be the golf balls, and this would be the ping pong balls, I would know that this would have the same number of balls in it in this configuration. I hope that that makes sense. This is, I know, kind of a tricky concept, but basically, if one atom or molecule is twice as massive as another, you can have the same amount of mass with half as many molecules. That's all that we're saying. And of course, we know that the masses of the elements are all given in the periodic table. We talked about that previously. And so this is one of the things that makes the periodic table an essential tool for understanding how chemical reactions work. So let's look at the following example. We've got two different things. We've got atomic carbon, so just individual carbon atoms, and we have molecular hydrogen here, O2, two oxygen atoms bound together. And if we look at the periodic table, we can see the mass in AMU is listed for each one. So for carbon, it's about 12, and for oxygen, it's about 16. But we know that we've got two oxygens, so 2 times 16 gives us 32. So we've got 32 AMU for the oxygen molecule. And for the carbon molecule, we've got 12 AMU. Remember, AMU stands for atomic mass units, and that's the mass unit that's given on the periodic table. And so we can say that a carbon atom is 12 over 32 as big as an oxygen, because a carbon atom has 12 and an oxygen has 32, so the ratio of those two would be 12 over 32. And of course, that fraction works out to be 3/8, because you can divide both of these by 4. And so 3/8 as big. So in other words, a carbon atom is 3/8 as big as an oxygen molecule. And so you can see on the scale here, here's obviously the carbon. And over here we have the oxygen in the beaker here. And we can see the rating on the scale, that for every 3 grams of carbon, there will be 8 grams of oxygen, and that means that they have the same number of molecules. So I've got the number of carbon atoms here is equal to the number of oxygen molecules. How can I figure that out? So if I need to make a chemical reaction involving these guys and I need equal numbers of atoms, I can just measure out 3 grams of carbon and 8 grams of molecular oxygen, and those are going to have the same number of atoms. And then we can talk about the number of atoms in the equations have to balance. Now, it turns out there's a very special number called Avogadro's number that relates the mass of a substance to its number of molecules or atoms. And that number is given right here. It's 6.02 times 10 to the 23rd. And so that would be basically, to do the times 10 to the 23rd, you would move the decimal place over to the right 23 times. And so that would be 602 and then 21 additional zeros after it. That's a really, really big number. And that number is what we call a mole. M-O-L-E, a mole. And so all a mole means is that number, 6.02 times 10 to the 23rd. Just like, how much is a dozen? A dozen is 12. How much is a couple? A couple is 2. How much is a mole? A mole is 6.02 times 10 to the 23rd. So that's just a word that represents this specific number, which turns out to be very useful in chemistry. And here we have a little picture of a cartoon animal mole. It's not the animal mole. It's just the number 6.02 times 10 to the 23rd. But if this little funny cartoon helps you remember the name, then that's great. But that's a mole. That's the animal a mole, the kind that, might dig up your yard and cause problems. But the mole that represents the number is 6.02 times 10 to the 23rd. Now, here is the cool thing about the mole. Let's consider 3 different elements off of the periodic table. So here we've got sodium, which has the chemical symbol Na. Here we have lead, which has the chemical symbol Pb. And we have helium, which has the chemical symbol He. And let's consider helium. Helium has an atomic mass of 4.003. Now, if I measure out 4.003 grams of helium, that is the amount of helium that contains 1 mole of helium atoms. So 1 mole of helium atoms weighs or has a mass of 4.003 grams. Now, lead is obviously much heavier than helium. Lead is a solid, helium is a gas. But if I look at lead on the periodic table, I see that it has an atomic mass unit of 207.2. 207.2, that's the atomic mass of a lead atom. And if I measure out 207.2 grams of lead, I know that's the amount of lead that contains 1 mole of lead atoms. Similarly with sodium, sodium doesn't weigh as much as lead. It weighs more than helium, but not as much as lead. So if I measure out this, so here if I look at sodium again, I've got 22.990 is the atomic mass of sodium. If I measure out 22.990 grams of sodium, I know that's the amount of sodium that contains 1 mole of sodium atoms. In other words, 6.02 times 10 to the 23rd sodium atoms, or 1 mole of sodium atoms. Now let's look at how this applies to a chemical equation. Here I've got 2 hydrogen molecules, 2H2, plus 1 oxygen molecule, 1O2, yields 2 water molecules, or 2 H2O. Now, this 2 here tells me that I've got 2 moles, and that is going to be 4 grams. And so 2 moles means 6.02 times 2 times 10 to the 23rd, or 12.04 times 10 to the 23rd molecules. Here, I've got 1 mole of O2, which is 32 grams, and that's going to give me 6.02 times 10 to the 23rd molecules. 1 mole. Here I've got 2 moles, which is double. That's why it's 12.04. Here I've got 6.02. And then this guy here tells me I've got 2 moles of water molecules. And again, that gives me 12.04 times 10 to the 23rd molecules. Okay, so let's look at another example. How many moles are there in 45.5 grams of chlorine gas? Okay, so if we look up chlorine on the periodic table, we find that chlorine has an atomic mass of 35.5. So that's 35.5 AMU. Now we also know that chlorine bonds together and forms Cl2. So we know that the total mass in a chlorine molecule is going to be double this, 35.5 times 2. That gives me 71 AMU. And so that is how many grams needed to make 1 mole. So it's 71 AMU. That's the mass of chlorine gas. So we need 71 grams to make 1 mole. Now, we don't have 71 grams. We only have 45.5. So what percentage of a mole do we have? Well, we can simply divide and get a ratio. So in other words, we can say that what we have is 45.5 grams divided by 71 grams, and that equals 0.64. And so that's the percentage of a mole that we have. And so our answer is that 45.5 grams equals to 0.64 moles. I know that's a little bit tricky. You may want to rewind this video a little bit and watch this again if that's not clear, but hopefully everything that I just went through makes sense. Okay, let's look at another example. How many grams of water are produced from 1.25 moles of methane? Given that the chemical reaction is that 1 mole of methane plus 2 moles of oxygen gives 2 moles of water plus 1 mole of carbon dioxide. So this is actually a pretty tricky problem. This is maybe one of the trickiest problems we're going to do this whole course. So the first thing that we want to look at is we've got 1 mole of methane produces 2 moles of water. So 1.25 moles of methane are going to produce 2.5 moles of water. How do I know that? Because the ratio is 1 mole gives 2 moles, so 1.25 is going to give twice that, or 2.5 moles of water. Now all we have to do is figure out how many grams of water there are in 2.5 moles. So let's consider water again. We know we have H2O, and we know that the atomic mass of hydrogen is 1, and we have 2 of them. The atomic mass of oxygen is 16, so we've got 2 plus 16 gives 18 AMU for water, and that means that there is 18 grams in 1 mole of water. Now, if we have 2.5 moles, we're going to take 2.5 times 18, and 2.5 times 18 gives us 45. So the answer is that 1.25 moles of methane gives 45 grams of water in this particular chemical reaction. All right, let's look at another example. How many moles of carbon dioxide, this is the carbon dioxide, how many moles of carbon dioxide are produced from 50 grams of methane? So we know in this reaction we've got 1 mole of methane plus 2 moles of O2 gives us 2 moles of water plus 1 mole of carbon dioxide. And so for every mole of methane that is input into the reaction, you end up with 1 mole of carbon dioxide output from the reaction. So all we really need to do is figure out how many moles there are in 50 grams of methane. So how many moles are there in 50 grams of methane? So let's start out. We've got methane is CH4, and we've got 1 mole of it. Now, the atomic mass of carbon is 12, and the atomic mass of H4 is about 4, and so the atomic mass of CH4 is 16. And so for 1 mole of CH4, that's going to be 16 grams, and that gives us 1 mole of CH4. Now, what are we going to do with that? We know we've got 50 grams, and so if there's 16 grams per mole, if we divide 50 grams by 16 grams per mole, 50 divided by 16, 50 divided by 16 is equal to 3.13, and so that's how many moles we have, 3.13 moles. And that is the last example we're going to do in this video, but we'll have another video where we finish talking about the rest of the material in the chapter.